We are at chapter 27, section 2, multi-loop circuits. And in this section, we are going to use what we learned from the previous section in the single loop, because we really covered all the concepts and rules. Now we are going to apply them in more complex circuits. And here what we have is there are three resistors, R1, R2, and R3, and they are connected in parallel. So what we know is from chapter 25 even, right? We started the circuits then with capacitors. So if we have a parallel connection, we know that V is the same. And for the series connections, we have the charge is the same since charge is related to current, and we have more resistors. We're going to think about the current instead of the charge. But current stays the same because charge is conserved. Okay, so we are going to apply that. So we have a parallel circuit, three resistors connected parallel to the EMF source, as you can see here. And that means they will all have the same potential difference. So V's are going to be the same. And resistors in parallel have the same potential. The voltage V is the same. But they may have different currents depending on the resistance values. And in this example, first of all, this circuit has 4 different junctions, okay? And since we are getting only I1, I2, and I3 on each of them, so what you see is here there's I3 going that way, and if you focus on this junction here, I3 is exiting, I2 is exiting, I2 plus I3 is joining to this junction. So that's why we label the current on this branch here between these two junctions as I2 plus I3 instead of calling it something else. And here on this junction at the bottom, similar way, kind of opposite to what's going on in the upper junction. I2 and I3 are coming in, and I2 plus I3 is coming out. So we already kind of applied a junction rule there to figure this junction current value on this branch as well. And if you focus on the other junction, so I'm going to draw it like this. So this one here, you can see that I1 is going out, I2 plus I3 is going out, and I is coming in. Then we can say that I is coming in, what comes in goes out, right? And that's I1 plus I2 plus I3. So we label the current on the main branch. When I say main branch, I mean where the power sources, EMF, that's I, and I at that blue junction goes in, and it splits up into I1 and I2 plus I3, and then I2 plus I3 at this junction here will also split up into I2 and I3, and those are the currents on each resistor. Okay, so current adds up on a parallel circuit, just like charge would add up, and the voltages stay the same. Okay, so that's what we see in the parallel circuit. But multi-loop circuits are not going to be always parallel, so we are going to go through some examples, and we will see more details. So here's our multi-loop circuit again, and we said that voltages stay the same and currents adds up. So if you think about the current, let's think about I1 on R1, right? And we know that Ohm's law is V is equal to IR. Using this, remember that we use Q is equal to CV, the electrical equation for capacitor, as many times as we needed. Now we have Ohm's law, and this is the electrical equation for resistance, and we are going to use this as many times as we need. So if you think about I1, since voltages are the same and simply V, which is that EMF, open circuit voltage, and we have that V over R1 for current, and that's I1. Okay, so you're going to be consistent, and that comes from, again, Ohm's law, that electrical equation for the resistance. And if you write down what the main branch current is, I equals to I1 plus I2 plus I3, and that is V divide by R1. You can see the example of the current we just wrote. We will do the same thing for the other ones too. So it's going to be V over R2. V's are the same again because they're connected parallel. And you can take the common factor out, and this becomes R1, 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so this is the main current. And again, if you think about what the current is, it's V over R. So I is equal to, so thinking about Ohm's law of this equation, I have I here. On the other side, I have V, and over R is this, right? So this is really equal to 1 over equivalent resistance. So then we can get what that equivalent resistance is. So it is 1 over equivalent resistance is equal to that inverse is added. And that is the reason in parallel circuit, parallel resistors, we will add up the inverses. And again, don't forget to take the inverse again to find equivalent resistance. And this is what we did for series connected capacitors, right? We did add up the inverses for the series connection for the capacitors, but we do the similar algebra for resistors in the parallel connection. Okay, so that's kind of the difference. And so this is the parallel case, and we know that in series we simply add them up. So we do kind of summarize all these things here, and you can see the differences and the similarities. These are series and these are parallel, and you can see that the series and parallel are similar, right, in the capacitors, and then you can see that 1 over inverses. And also in the parallel, capacitor is similar to the series like connected resistors. You just simply add them up. What doesn't change is, again, the same charge for series. That means same current, same potential difference for parallel, same potential difference for parallel. Those two concepts don't change. But for capacitors, we are focusing on the charge because we know that Q is equal to CV. This is how we relate the Q and V. And for resistors, we have V is equal to IR. So that is how we relate the voltage to current. So that's why we need to switch our minds to current. But we know that Q is equal to, actually, let's say I is equal to dQ over dt. So that's why there's a relation between these two, and that's why these are the electrical equations that we are using in our multi-loops in any circuit.